Newell and Simon debuted their logic theorist here. And overall, these people spent a lot of time, I think like about a month in this, just talking and brainstorming ideas, and a field was more or less born out of this. So this is credited, even though there obviously is work that predates it, this is credited as being kind of the originator of artificial intelligence as a field. And finally, the last thing I'm going to talk about in the 50s at least is that Frank Rosenblatt at IBM, I believe, also, developed a perceptron, what he called the perceptron machine. Okay, the perceptron machine was a hardware machine at the time. It wasn't done in software, but essentially it was implementing an algorithm that would take images, in this case images of characters, and use this algorithm, which is really a machine learning algorithm that is not that different from what people use today. Frankly, it's very, very similar, to learn to classify English letters from their images. All right, so this is now within the first 10 years of computers really being available, period. And they were available in the 40s a little bit, but the first time of computers being available, within 10 years of sort of this Turing test being proposed, there had been progress on game playing, logic and automated reasoning, AI as a field, and then also machine learning. With incredibly rudimentary hardware that's nothing like what we have today, this was all developed within the first 10 years. Now, AI, in the course of history, AI has certain trends of AI have waxed and waned. There's been more interest in logic at first, and then more interest in machine learning now. But these things were all, these are not new ideas fundamentally. These all came about during this time here. And it was sort of this amazing time for laying the framework of what we all still are doing now. So now I'm going to talk about a couple other notable things that happened including some videos, a couple notable things that happened in AI. But I'm really not going to, this is not, as I said, this is not even close to an exhaustive list. These are a couple of things that I kind of find myself fun, and they're fun to show. But after this, these next things, you can pick and choose, however, whichever ones you want, whichever ones sort of are most interesting to you. So, in 1966, Joseph Weisbach developed Eliza. Who here has heard of Eliza, by the way? Not that many. OK, great. So I'll get to show you all scripts from Eliza. What Eliza was what's called a chatterbot now. They didn't have that term then. But essentially, it's a computer that will talk to you. So you talk with a computer, much like a Turing test. But as you'll see, it can't quite pass a Turing test then or now. And Eliza was developed as kind of a virtual therapist program, which is very useful because therapists are very easy to code because they never actually answer anything, right? They just ask you questions back when you ask a question. So this was a program, and actually he wrote this program almost kind of as a sign of what couldn't be intelligent. Of course this isn't intelligent, but yet it was taken seriously by a lot of people. And so this very rudimentary kind of pattern matching and simple language processing actually inspired a lot of future work. So I'm going to show you a couple transcripts from Eliza, including the one that first was published along with the Eliza paper in the Communications of the ACM. So this is a conversation of a young woman with Eliza. Eliza's responses here are in capital letters, and her questions or comments are in lowercase. So she comes and goes to the terminal and says, "Men are all alike." And Eliza says, "In what way?" "They're always bugging us about something or other." "Can you think of a specific example?" "Well, my boyfriend made me come here." "Your boyfriend made you come here?" I don't know if that was a question or a comment. And she says, "I'm depressed much of the time." "I am sorry to hear you are depressed. It's true, I am unhappy." "Do you think coming here will help you not to be unhappy?" "I need some help, that much seems certain." "What would it mean to you if you got some help?" "Perhaps I could learn to get along with my mother. Tell me more about your family." And this is pretty good. right? I mean, this is actually, I could imagine this actually happening I mean, it would be a little bit odd, right? But if you suspend your disbelief and just think of it as a conversation, this is totally plausible. What you will find if you interact with Eliza, and you can, by the way, there's lots of links to current Eliza programs that more or less follow the original program here, is that it quickly gets very frustrating unless you really are willing to either get lucky and talk about your family, which has a lot of keywords for family and mothers and fathers and stuff like that. You'll quickly kind of hit some barriers that are kind of frustrating. So here was my conversation with Eliza, which I started. I said, hello. And it says, how do you do? Please state your problem. I am worried that I'm just speaking to a computer. Do computers worry you? No, but I'm trying to discern if you are a real person or a computer. Are you just saying no to be negative? Are you saying no just to be negative? You did not address my question. Your question. I think this is a question here. So it says your question, question mark. Are you a computer? And then it goes back to, do computers worry you? and it will go on this forever, of course. It will keep going. So the illusion breaks down pretty fast, right? Yeah. At the same time, this was sort of at the time this was this great breakthrough. I wouldn't call it a breakthrough again because it was known to be kind of a bunch of clever hacks together. But it was this interesting thing that you could actually program a computer with some pretty rudimentary knowledge, and this would create something like a conversation. And I think these examples generated a lot of initial optimism about, and I'll have a quote at the very end about how soon people thought they were going to be able to develop general purpose AI systems. It was very soon. And I think this kind of stuff really kind of cemented that, right? Because these things look plausible, and they look like, wow, we're really getting there. Taking a different tack now. That was Eliza was sort of a purely a program you'd interact with through a terminal. There was also concurrently a lot of progress in robotics at this time. So one of the first general purpose robots was this robot called Shaky, developed at Stanford Research Institute. And the goal of this was to develop a general purpose robot that's capable of interacting and reasoning with the world. I'm going to play a video now about Shaky the robot. It's about 5 minutes long, so it's a little bit long, but really it covers so many things that I think it's just this great, again, this is 1966, it's this great encapsulation of what a lot of AI is still about. And they were already thinking about these things 50 years ago. So let's start playing this thing. Oh, I don't have, sorry. Let me back up, see if this works. Okay, well, we'll see if this plays. No. All right.
Some of the abilities associated with abilities like planning and learning. Even though the tasks we give Shaky seem quite simple, the programs needed to plan and coordinate his activities are complex. The main purpose of our research is to learn how to design these programs so that robots can be employed in a variety of tasks, ranging from space exploration to industrial automation. Shaky operates in this experimental environment of rooms, doorways, and simple objects. In our first task for Shaky, we want him to use this box to block this door, starting from this position. The robot executive is capable of understanding a wide variety of English statements, questions, and commands. We can type Shaky's first task in English, which is translated into predicate calculus, the language used by Strips. Strips analyzes the task and produces a plan to solve it. Let's diagram the plan found by Strips. First, Shaky plans to use the action go to D5 that will take him to the doorway. Then he will use the actions go through D5 and go to D3. Finally, he plans to use go through D3 and block D4 with box 1. After computing the plan, Shaky begins to execute it. He moves to the first doorway by using the action go to D5.
So robots are still this slow, but the trick now is we speed up the video more to make them look faster, I guess, is the only difference.
He looks through the doorway because he is uncertain about the contents of the next room. His view of the floor along his path shows no obstructions, so he moves into the next room by using the action go through D5. But just after this move, Charlie the Gremlin blocks the next doorway with a box. Shaky doesn't know it yet, but the box is right in his planned path. Because the contents of this room are unknown, he checks the next leg of his journey with a television camera. The box is in Shaky's field of view. This is how it appears on a TV monitor. Shaky's vision programs analyze the picture and tell him that his path to the doorway is obstructed. He takes another TV picture of the obstructing object. Here we monitor on the cathode ray tube display the results of vision programs that enhance edges, identify the main regions of the scene, and determine the location of the box on the floor. Once located, the object that blocks his path can be entered in Shaky's model and given a name, Box 2. Now Shaky realizes that he cannot carry out the original version of his plan. His first recourse is to see if some other version of the old plan might work. Shaky remembers the form of the plan and can substitute other symbols into the same form to produce another version of the plan. In this case, Shaky was fortunate. The new version will solve his problem. Otherwise, he would have had to use strips to make a brand new plan, possibly one that used the unblock action to clear the doorway. Here, though, strips was not needed, so Shaky begins to execute the new version of the old plan. First, he turns and goes to another door.
All right, I'm going to stop it here. If you are in huge suspense, Shaky does in fact push the box into the blocking door. You can see the video on YouTube. It's about 20 minutes long, but it's really cool because it is really this case of quite complex plans and actions done again 50 years ago now, almost. And I think a lot of AI is still looking at similar problems. Now, we have moved quite a bit beyond that. It's not as if we are still doing this. But a lot of those same problems, this sort of problem of having a robot, for example, that will interact in an environment with normal users, that's still one of the key challenges facing AI. So next thing I want to mention, because this is also a very cool video, is some work done, and CMU can claim some of this, because Mark Raybert was here at CMU for a while before leaving for MIT, though I think this video is from MIT. And this bit, one thing you know about Shaky, right, is that Shaky was moving. It was sort of impressive what he was doing in some sense intelligently, right, because he was replanning, looking at his environment, interacting. But the actual movement of Shaky was pretty shaky, to put it one way, right? That is in fact his name. And so it wasn't long after, though, that people started developing more the hardware of robots. And this work by Mark Raybert here at MIT is very famous for being kind of one of the most impressive demonstrations of what robots could do at the time. Mark has since gone on to found Boston Dynamics, which makes the Big Dog robot and the Petman robot, which you might have seen on YouTube at some point. These are more impressive than this, but given the time, I think that is the date that these were created. I think these are very impressive as well. So this is a shorter video.
This was developed by Mark Raybert, who founded the MIT Leg Laboratory in the 1980s. To keep this simple, he started with one-legged robots.
So we built one-legged machines. They actually hopped on the block. And we found that the control of these machines wasn't really too difficult.
The robot had sensors which measured its motion and had a computer brain which used this information to reposition the leg between hops. The computer calculated where the legs should move to keep it balanced. Like all Raybert's dynamic robots, they had to keep moving to stay on their feet. His dynamic robots performed amazing feats.
Okay, so again, a couple demonstrations there about the kind of stuff that robots were doing, again, 25 years ago now. 35 years ago, sorry. Never keep track of what dates are what. All right, so I'm going to now talk about a few more things that are, again, kind of milestones. I don't have any more videos. These are a little bit more maybe just historical, but were very sort of pivotal in the development of AI as a field. So what happened in AI is, and I think this is, I don't think I'm too controversial saying this, is that during this initial enthusiasm, people had these wild expectations for how AI was going to develop. And the predominant thinking was that AI would work by essentially doing things like logic and manipulating symbols and doing reasoning in order to deduce conclusions from basic premises, essentially how you do deduction in mathematics. And this was sort of the thinking of the time. And despite this sort of the potential of all of this, it became known soon thereafter that these problems were actually NP hard. So it was actually very hard to solve some of these problems. And the toy examples that people were showing kind of amazing performance on, things like Principia Mathematica, these were not going to scale to the extent that maybe we hoped for initially. Right? And so around the 80s, a little bit different trend in AI came about, which is what became this topic of machine learning. But the idea here, and again, this dates back to the original perception algorithm, though it went out of fashion for a little while, is that the idea here was that instead of trying to encode kind of pure thought or logic as the means to an end, we might take cues instead from how our brains work. Not necessarily try to make things like our brains, but take some cues from that. And this led to an algorithm called a neural network. And we'll talk a little bit about neural networks in this course. Neural networks are making another comeback now. They've sort of made two comebacks, and they're right in the midst of another one. They're hugely popular right now. But what happened in the 80s was that the neural networks became popular, and particularly backpropagation as a way to train neural networks to make them learn from data became a popular algorithm. Popularized by David Rumelhart and John Hopfield, among many others, but these sort of became kind of what people did in neural network machine learning. Later on, though, I think a lot of the initial work in AI focused largely on concrete knowledge, right? Things that were true always. And in the 80s, the influence of Judea Pearl and others, so again, these things do date back farther than that, started to become a lot more felt in AI. So in '88, Judea Pearl published a book called Probabilistic Reasoning in Intelligent Systems, and that really introduced, or at least laid a lot of the foundation for probability and Bayesian networks being at the forefront of AI. And we will talk about both probabilistic reasoning and Bayesian networks, because the reality is a lot of the classical methods in AI, like Shaky's methods, they really worked with yes or no answers, right? They were logical systems, and in order to interact with the real world, the thought was, well, the real world is not quite that concrete. We need systems that will be able to act probabilistically. A couple other big milestones. In '97, Deep Blue defeated Garry Kasparov in chess. You'll notice those original pictures we had, I think, of Newell and Simon and of John McCarthy. They were both playing chess in those pictures. So chess was seen as this grand challenge for computers because it seemed to require intelligence, right? It's a game, the rules are well defined, yet it seems to require intelligence to be able to actually play. And in '97, Deep Blue was for the first time able to beat a world champion at chess. And again, there is some debate over whether this really constitutes intelligence or not. What Deep Blue was doing was it was using a massive amount of computing, at least for the time a massive amount, to simulate a bunch of possible games and exactly the kind of methods we're going to learn about in this course, and would just have a lot more power than Gary Kasparov, right? There's no way he could simulate that many things at the same time. And so all his situational awareness and intelligence, in some sense, couldn't quite match up against that just the sort of the brute force solution there. So one thing, and this is sort of important because it does sort of also typify a common theme in AI, being that something requires intelligence until it doesn't anymore, right? So for a long time, chess was the prime example of an intelligent system. Of course you couldn't play chess without intelligence. Once we solved it, though, we realized, well, no, that's not quite intelligence anymore. And this is actually a common thread amongst a lot of AI, right? Because once we understand something, the inclination is to label it, well, that couldn't really be true intelligence. Intelligence is still this murky thing that we can't quite define. But I think we're getting to the point where it's hard to really say that with a straight face anymore, because these things are so good at what they do, and I'll show a few more examples later. Current systems are so good at what they do, things that we use intelligence for, and they are so good at it that it's hard to say, well, the combination of all these things is unintelligent. I think that's a hard case to make these days. A few more things, again, bringing CMU and also Stanford to the forefront here. In 2005 and 2007, Stanford and then CMU won these two, first Stanford won, then CMU won these two contests run by DARPA to drive a car autonomously. In the first case, in 2005, they were driving a car through the desert, through like a desert trail. The second case, they were driving through a simulated city. It was actually on a military base. It wasn't a real city, though, as we all probably know now Google is, in fact, driving cars in the city and seems to be continuing this work very well. They've, in fact, a lot of people from MIT and or from CMU and Stanford have since left to go work there. So this is, again, something where I think clearly driving a car requires intelligence, right? Everything that a car involves, so not just the control of the steering wheel, but figuring out your situation, what other cars are, where the pedestrians are, what's the right thing to do in different traffic situations. This clearly requires intelligence, you may say. But once you build a system, the temptation is to say, well, no, it's just a bunch of rules. And I think that the current thinking is that it's OK. What we're concerned about is accomplishing solving these hard problems. And we don't really care too much whether or not it's some sort of fuzzy intelligence or not, because these things, in some sense, just clearly are intelligence. They clearly are smart systems. Similarly, in 2011, this is the last one I'll say of the history at least, IBM's Watson beat the human opponents in Jeopardy! It made some sort of well-known mistakes, too. You might have seen the mistakes it made. Like it asked what U.S. city has some airport or something, and it said Toronto, and Toronto's not a U.S. city. But it did beat them, and it waited very little on that because I wasn't very sure about that one. There's also, I think, some question of whether it just was able to buzz in faster, but it's still very impressive, right? It's able to just get the questions in plain text English, use a database to figure out what it's doing, all an internal database, and then answer questions from that. And the last thing I'll say is that really AI is all around us now. What we call AI has taken a hold in things like face detection. If you bring up your camera, it will put a box around people's faces. It's running a machine learning algorithm to do that. This is an example of AI. Personal assistants, so Siri on your phone or Google Now, they're using a whole lot of speech recognition and then natural language processing to figure out what you're asking it and give you hopefully a good response. Again, with the Turing test, I don't think Siri would fool anyone into thinking that it was a human, but it still can be useful, right? And similarly with oops, I actually meant this is supposed to be machine translation here, not I changed my figure at the last point, but machine translation is Google Translate, translating some illegible English here to Chinese. Logistics planning, how do you schedule all these vehicles so that we can order a package and have it here the next day? That's actually a very hard problem, right? Just from a standpoint of many millions of packages being shipped every day, how do we do that? Now, all these things really do use techniques developed in the field of AI. Whether or not they are intelligent is debatable, but I think it's actually not the right question at all. The question is it useful? And does it require techniques that seem to address similar problems as does intelligence? And the answer for all of these is obviously yes. Right? They require things that seem to need some form or another of intelligence. And that's all we're really going to worry about in this class. We're not going to worry too much about the philosophical issues of, well, are these boxes really intelligent or not? So, having said all that, now let me dive into the logistics of the course. Are there any questions about the history of AI? You can ask them on the Piazza board. In a class this big, I know it's sort of intimidating to ask questions sometimes. That's why we have the board. In fact, you're required to use Piazza, so you will have to maybe not ask questions. You have to at least respond to questions. So, as you've probably seen from the syllabus, and we have a syllabus posted on the website, by the way. The website is here. It should be also on the class page, on the registrar's webpage. So you should be able to have already seen it. Bookmark it, because it's kind of a long thing, I know. But it'll have the syllabus. It'll have all the lectures. So we'll have slides from the lectures on it. And it will also have videos for the lectures, as much as we can. We're doing it ourselves. This is meant largely as just a resource for you to go back if you sort of want to re-look at something that was presented in the lecture. Videos are online. They're not intended as a substitute for lectures. In fact, you're required to come to lectures because you have to actually answer some in-class questions. But they are a resource there for you if you want it. So what we're going to cover in this class includes uninformed and informed search, numerical optimization, constraint satisfaction, integer programming, machine learning, classical planning, probabilistic planning and reinforcement learning, probabilistic reasoning, computer vision, robot motion planning, scheduling, natural language processing, and multi-agent systems. OK. It's hard to even say, let alone do in one semester. What you will find is that there are entire courses on all these topics here at CMU. What this course is designed as is essentially an introduction to all these things for people who want to get that introduction without first spending a whole semester in each one of them. They're all very useful things, and you can invest, forget a semester, you can invest your entire career studying any of them. But if you are busy students, master's students, undergrads, graduate students, you might not want to do that, invest your career ahead of time, right? You might want to just get some sampling of everything. That's what this course is for. So this course is meant to be a sampling of all these different topics. That being said, it is going to be somewhat intensive. It is a graduate level course. There's an undergrad version of AI as well. And this course is going to be substantially harder than that one. It's just a graduate course. So despite the fact that these are going to cover a lot of things, in a lot of them, you will be required to actually implement things, to actually derive equations and expressions here, and program them. So this is not a learn about the ideas here. This is about implementing the ideas. In the next class, we'll talk much more about the precise things you're going to want to implement, and languages you might need to know, and stuff like that, and a more detailed schedule for the class. But all I'm going to say here is that this is the broad range of topics, and this is what you're going to be expected to come out knowing and having some experience with all of these things. All right, so now I didn't actually introduce myself ever, I realized, as I was giving this lecture. But I figured I shouldn't stop myself because I was, on a roll, maybe. But I'm Zico, Zico Coulter. The other I'm one of the two instructors of this course. The other one is Zach Rubenstein, who is there. And the TA is Vittorio Pereira. That's how you pronounce your last name? Yeah. OK, great. We will be your point of interaction to this course, obviously. I will be giving half the lectures. Zach will be giving half the lectures. Professor Rubenstein, either one is fine with me, actually. Does not matter. Yeah, be respectful. If you want to say Professor Zico, Professor Coulter, it doesn't matter to me. We will each have office hours. The office hours are on the web page now. They weren't for a while, but they are now. Zach and I will have office hours directly after class. So today, after class, I will have my office hours. That is intentional. If office hours are separate, we find that oftentimes people don't ever bother coming to them. It's just an effort to make it in and come to an office. So my office hours are right after class today, and Zach's will be after class on Wednesdays. Mine are always after Mondays, his are always after Wednesdays. They're listed in our offices. My office is in Gates on the 7th floor, and his is in Newell Simon, but we will walk over there after class, so you're welcome to walk with us. Maybe we'll just hang out here, in fact, if there's too big of a crowd to fit in an office. In addition, Vittorio's holding office hours on Tuesdays and Thursdays, every Tuesday and Thursday from 1:30 to 3. So do use those resources. You are also welcome to use Piazza as a forum for interacting with us. We will try to answer your questions within 24 hours of posting them to Piazza. Hopefully faster if it's urgent, but we don't guarantee being faster. So also answer each other's questions, because that can be useful as well. Is Piazza next? No, I think I have some. Sorry. A few more slides, and then I'll actually describe what Piazza is, and we'll even run a quick little demo of it. OK, so one question we've gotten a lot from this class is what background you need to actually take the course. There are no formal prerequisites. By that, I mean just that we do not require you to have completed course X at CMU in order to sign up or get some exception. A lot of people here are master's or PhD students. They've probably taken similar courses elsewhere. So it would be silly to require a CMU undergrad programming course. That being said, this course requires programming. We're going to do assignments in Python. Chances are, if you are very good at programming but have not ever used Python before, you will be able to learn it for this course. It's meant to be a very easy language to learn. But at the same time, if you do not have any programming background, the chances of you being able to complete the assignments is very small. Just, it's life. This is a programming course. It's a computer science, advanced computer science graduate course. You have to program. Besides that, though, other background is mostly optional, I think. Maybe we'll find as we go through if that's really the case or not, but we're at least trying to make it be the other background is optional. You probably need some math background. We will do some proofs in this course. It's not just it's not math free. There's plenty of math. But if you have a basic mathematical background, you've taken undergrad math, undergrad calculus, linear algebra, or probability, either or all of those, you probably will be OK. Again, I don't know for sure, but that's our hope, is to not overload math component, though still keep some math there, because you can't avoid math when you talk about optimization and machine learning and these kind of things. So if you know some data structure and algorithms, if you know linear algebra, if you know probability, that's great. It will be very helpful. But hopefully you will not be unable to do the course without it. Next, the textbook. There is a textbook for this course. Actually, has anyone checked to see if it's in the bookstore? Is it there? Has anyone bought it there? No one's even bought it there. That's great. So you probably shouldn't. You probably just get it from Amazon anyway, right? It's probably cheaper there. I don't know that for sure, but maybe it is. It's Artificial Intelligence, a Modern Approach. This is the standard textbook for AI courses. I think probably 50% of the courses on AI use this textbook. And we are having it be the official textbook because there is a lot of information that's covered there that we're going to cover in the course, and we want to give you that resource. That being said, we're not following this textbook at all, kind of chapter by chapter or anything like that. And there are some sections in this course that are going to be additional material that's not discussed in the textbook. So things like numerical optimization is not mentioned very much in this textbook, but yet optimization is kind of actually a fundamental principle behind a lot of current methods in AI. And so we are going to have a unit on numerical optimization separate from what's in the textbook. And other things are similar, though the textbook has information on a wide variety of things like we're going to cover, like computer vision and natural language processing, et cetera. And there we'll try to at least cover some of the same materials in the textbook, so it will be a useful resource for you to read up on what we're talking about in class. If you have an older version, by the way, that's probably fine. Second edition is OK. I don't know, the first edition is pretty old, right? No. Second edition is fine. The first edition, probably time to upgrade. All right, and finally, the thing that I know is going to keep everyone wants to know, right? Is how to, okay, so what's the grading going to be for the course? The grading, this is the official breakdown for those that are curious, and we will stick to this. Problem sets, which we'll talk about in a second, are going to be worth 45% of the grade. Midterm is 20%. Course project is 25%, and class participation is 10%. I'll talk about what this means in a second, because no, you don't have to all ask questions and just make yourself heard in order to get that 10%. Problem sets. Okay, so problem sets. There are going to be 4 problem sets throughout the course. And these are really kind of one of the main components of the course, right? It is to test your knowledge of what we've taught you and show us, both test it and extend it, I guess, right? Because we're actually going to program stuff and derive stuff on these assignments. They will each have written and programming assignments. The written portions you'll turn in at the beginning of class every time. The programming parts will be turned in using AutoLab. AutoLab is a CMU automated grading system that will automate grading for the programming portions. Now, there's a few effects of this. It's very nice in some ways because you get to know beforehand whether or not, you get to know exactly what your grade is on the homework beforehand. The programming part of the homework beforehand, right? Because you can submit it as many times as you want before, see what score you get, if you do pass or fail, and you can see that. If you fail, you can submit again. But the downside is that it's not quite as helpful. You know, if you have no idea how to approach a problem, and you just write some random stuff as you might, to turn in when you're turning in code on paper, you will get no credit. Because what matters is what actually the computer says how well your code does. So it will force you to actually solve the problems, and it can also mean sometimes that there might be small bugs that make everything look right, but cause some issues. We will try very hard to resolve these, but these things do come up. With automated grading, I think the benefit ultimately outweighs the downsides of it, though. Who here has used AutoLab before, actually, by a show of hands? OK, great. So there's some experience with it. So some people at least will be. And then you can maybe help the other folks that haven't before. Very important. I'll mention this again one more time. But you can discuss problem sets in groups. It's encouraged, in fact, because one of the best ways of learning is to use this material, is to go over it in groups. That being said, it is very important that you write up and both written parts and code independently. Okay, so go to your group discussion. This is a very standard policy, I think, in a lot of classes these days. The policy is you can discuss them, go talk with your classmates about what the problems are about, try to figure them out together. Then when you're going to write them, take all those notes and put them aside and rederive it all from scratch on your own for the written portion. It's very important, especially in programming. If you submit 2 things that are the same in programming, AutoLab will know exactly. Other times you might get by a few times because it's human, error-prone humans that are looking at stuff, but that's still not allowed, and there's a good chance we will find it. So please write up your homeworks independently. I'm not going to talk about today the midterm of the course project. The course project we'll talk about more about next week. We'll have a separate document that describes that sort of says, lies down the expectations there and what that's all about. But there will be no final for this course. The final is, the course project is in lieu of the final. And that will involve a substantial, near research level project that we'll work on in groups. And the idea there is to delve very deeply into some particular area of AI. Very likely, and in fact, it's very encouraged if it is related to your separate research outside of this course. That's wonderful if you want to do that. It doesn't have to be also, by the way. You can pick some fun project that's just for this course. But we'll talk about that in a couple more classes. You should start thinking, that can be done in groups, and so you should start thinking already about what you might want to do for a final project and who you might want to work with if you want to do that. You can also do it by yourself, though, if you want. And on the final slot time, instead of the final, we'll have a poster presentation for the class projects. This is all pretty standard again. I think you've seen this in other courses before. There will be a midterm, though. And the midterm will be in class. It's on the schedule that's in the syllabus right now. So the midterm will be in class. It's designed to take about an hour. It will be designed to take an hour, but you will have the whole class period to do it. So hopefully people aren't too freaked out about that. Yeah? Oh, yeah, no question. OK. Yeah?
Regarding the problem sets?
Yes.
I mean, are the programming assignments independent of the problem sets? Or
No, they are all together in a bunch, and they're due the same time. So one of the problems on the problem set will be a programming assignment. that you will just have to turn into auto lab by the same deadline as the when you turn in the paper portion.
Okay, so basically there are like 4 assignments and 4 deadlines.
Yes, exactly. And those deadlines should all be on the syllabus too. Okay, so class participation. This we'll get to Piazza in a second, but class participation is this 10% of your grade. And it's going to be measured in 2 ways. So this is a fairly big class. We'll see how many people sort of drop out as time goes, but at least right now it's fairly big. There also, by the way, is a lot of people on the wait list still. So if you are, I mentioned this in the email, but if you are planning to drop out, please do that soon so people can get in officially and don't have to fret about getting off the wait list. I should mention that also here, I said this in the email as well, we will make every effort possible to get everyone that wants to take this course into this course. So if you're on the wait list, even if you're number 30, try not to worry too much. We will try very hard to get you into the course officially. It might take a few weeks, but we will try. Do our very, very best to do this. And because of that, please continue to come to all the courses if you are on the wait list as well. Because if you don't come to the courses, then you can't participate in the class, and so then you start lowering your grade there, and you don't want to come back, so it just builds up a vicious circle. So please come to the course. We will try to accommodate everyone, even if it means, you know, adding more chairs. I guess we can't do that legally, but we'll figure something out. So please come to the course. Class participation is going to be measured through, in fact, it's very important you come because this is going to be measured through participation in in-class polls. So we're going to use Piazza, at least in some of the lectures, we're going to use Piazza to ask everyone questions, and you have to respond to them. So we'll ask you a question, you'll say, you know, A, B, multiple choice questions, and you just check which one you think is right. We'll do this in a second, actually. We'll go through it right now in a second. So you'll see what it will look like. And you have to answer. And in fact, half your grade here will just be the fact that you do answer. You could always select answer A, and you get 50% of class participation grade. It's just, we want you to be here, and we want you to participate, think. And the reality is no one's going to do that. You'll think about the answer to the question if you're asked it and have to respond to it. So you have to answer half of them. The rest, the other 50%, will be, do you get them right or not? You know, imagine that, actually caring about which answers you get. But if you don't get them all right, A, if you get enough right, it counts for 100% of that remaining 50%. And you can also boost this bit here by participating in the forums on Piazza, in particular answering or asking other questions. Answering in particular, we would really like that, if you could answer other people's questions. But the idea there with Piazza is that it's meant to be kind of a general forum. So we want you to be participating in it. We want you to be answering and thinking about other questions, seeing other questions, and using that as a resource to have this discussion amongst everyone in the class. So Piazza now. Who here has used Piazza before? OK, good, about half. Who here has signed up for Piazza for this course? OK, so not everyone. So who here has a phone or a laptop with them and is not signed up? OK, so if you are doing that, take a chance right now to sign up for Piazza. Maybe while I'm doing this next bit, because you won't be able to actually participate in it, so please sign up right now. You have to do 2 things. You have to sign up for Piazza, and you have to download either the Piazza app on your phone or bring a laptop to class. Is there anyone, by the way, if you cannot do either of those, come see us. That's fine. My guess is that everyone can probably do one of those 2. Just chances are everyone either has a laptop or a smartphone. So we're going to use the app or the Piazza interface or an app in class, and we'll see how we do that in a second. So you have to bring one of those to class to answer the questions, or you will not be able to get that 50% for just answering questions because you will not be able to answer questions. Because of this, and this is very important, and this is sort of a sign that you are actually serious to us, for those who are not signed up by Piazza, by the beginning of next class next week, you will be dropped from the course. So just there's the threat right there, right? So please, please sign up. It is part of the course. It is part of your grade. You have to sign up to participate in the class. We'll see if we follow through on that. I think we probably will, because I think it'll be a small amount. But this is also to make room for those that are on the wait list, have signed up in fact for Piazza. Yeah?
Do we have to sign up with our CMU email address?
If you can sign up your Andrew with your Andrew ID, or with your Andrew email address, it's a little bit easier, because then we can correlate directly with the enrollment list. You don't have to, but it doesn't seem to be any more effort, so do if you can. Unless there's a good reason not to, please do. Okay, so let's see what this looks like now. So this is a class poll. Here is the Piazza interface that you will see during class. So I'm going to click hide poll results because I don't want people seeing it until we're done. And now I'm going to publish the poll. So this poll just asks about your background. This one, I have to say, well, this will not, in all fairness, this one will not count towards your grade. But it's a good debugging chance right now to see if you can actually do this. So for those that have signed up before, see and verify that you, in fact, saw that I just did that. So I just published the poll. You should pop up either on your, if you have an app, it should sort of pop up as a new poll. If it's on a screen, you should be able to just type it in. Is anyone, people seeing it? People are seeing it? OK, good. OK, so answer the question. What's your background? There's 3 votes so far, so not very many. 10 votes. Oh, great. This is great, huh? Oh, down to 9 now. I don't, did someone? OK, great. I think only like 25 people registered when or 28 were registered when I came to class. So, is anyone still trying to vote and hasn't been able to yet? Trying. OK. Piazza's being slow. OK. Hopefully we'll be able to debug these things, and maybe we could like get on the CMU network if the 3G doesn't work here or something like that. But all right, anyone still trying? This one isn't too important, but anyone still trying and unable to vote? This says loading. On your phone or on your laptop? OK. We'll give it a few more minutes. I want to, and it's fine because normally this questions will be longer and you'll have to actually work through them. So you think about them for a while and hopefully then it's loading and just says it's fine. So are you using the Piazza app or are you using the Piazza web page on your phone? Yeah. OK. OK, well, hopefully the app will get faster. I'll give it a few more minutes and then you can, if this still isn't working, you can try something else. All right, as I said, this one doesn't really matter, so we'll just do this now, and you can see what these kind of things look like. All right, close the poll. OK, so show poll results. All right, so here's the breakdown of students here. So a lot of computer science, computer science is a catch-all for people that are in computer science or other, MLD maybe or HCI. For robotics, there were enough separate ones that I put a separate one for this. There's a lot of robotics here. Electrical engineering is also very big. There were some other engineers here, and there's one other. So who was that? Someone was here. It had to be someone here, right, in the room? OK, it's all right. If you don't want to say, it's fine. But you have to be here somewhere, unless something's very strange. OK, I mean, maybe like architecture or something, right? So, all right. Let's just do one more, see if it works. Let's see. This poll is a multiple choice poll now. So rather than just picking one, you can pick what areas interest you most. So I'm going to publish this poll now. And it says which areas. These are a bunch of things that interest you. You check them if they interest you. You do not check it if it does not interest you. This one will take a little bit longer because, oops, I'm going to hide the results while we're voting. I'm going to feel really bad if the thing I was most excited about gets no votes and no one's excited about it. Typically, I'll give people about 5 minutes to answer these questions, depending on how complex they are. I mean, sometimes it's sort of a simple, did you get this or not? But they're quite valuable, I think, to get people to kind of interact more directly with material. And instead of just listening, you actually have to answer a question. And as I said, it will count towards your grade that you answer them. So if you're unable to get any, it's all just always loading, let me know because that would be a problem. We'll try to figure out what's going on with your setup. Oh, this is more, so this is great. 29 to 28. I guess people are. You can re-vote though. I guess this one. So if you check it accidentally, you can redo it. Maybe I'll put a timer up on these things so people know how much time they have. But for these ones, I'm not going to be very, very harsh. OK, well, this time I will end it now, close the poll, and show the results. So sorry if you got cut off here. But OK, so machine learning, non-surprisingly, is the most popular of all topics in AI. That was also borne out, by the way, in that word graph, right? So I like machine learning, too. I'm also a machine learning guy. Search and planning are very popular here. Numerical optimization, I'm sad to see, is not that, as you were saying. It's not that. I have to convince you all that numerical optimization is really exciting now. So I hopefully will. It really lies at the foundation of machine learning. So you will really learn to love this. And then there are other things as well. So OK, great. This is actually very useful for us because it sort of gives a nice, cool breakdown about what people actually like. OK, so a couple more things. I only have 5 minutes left, so just let me go through them quickly. Late days. This is also a very common thing. You probably had this in classes before. 4 problem sets. There are also some milestones for the project due. But stuff comes up in classes. You have some other deadline that's the same as this deadline. We don't want to penalize you too much for that. So you have 5 late days to use throughout the semester. This is the standard thing where a late day means extending the deadline for 24 hours. And just it's not like midnight the next night. Class is due at the beginning of class. So extend it to 1:30 the next day if you use 1 late day. You have 5 late days to use throughout the semester. And you can use no more than 3 on any given assignment. So you can't push the day back more than 3 days. And yes, weekends do count as days. They're not free weekends. If you are not able to turn in homework in class, you will turn it in Vittorio's office. If he is not there, slide it under the door. And regardless of whether he's there or not, write the time that you submit it on the paper. And that's bound. That time, by the way, is bound by the same honor code and academic integrity as everything else. Write the time that you submit it. So we know. Because frankly, when we look at them, we'll want to know when you're submitting it anyway, when we have all the things in a big pile. So please let us write on the thing when you're going to submit it. I think that covers all the things there. I don't want to miss anything because, again, the written homework should be due start of class, during class, programming assignments, start of class, submitted through AutoLab.
The late days will not apply to the final project.
That's one thing. Late days do not apply to the write-up for the final project. That's in the syllabus. I should have probably put it here, too. That's just because we need time to grade them. So you can use it for anything else, but don't use it for the final project. You will start getting points off the final project. I should say, again, also in the syllabus, if you violate this and go over your late days, you will start getting 20% off per day for each late day, for each day late you are. And we will be sticklers as much as we can about the exact times here, so don't try to push things. There's just a slippery slope then, so please try to get it on the actual times.
Also, my office is 7:00.
Oh.
But I'm usually in the lab on the 3rd floor.
Can they just put it in your office, though, or?
Yes, but they won't find me.
OK, so just slide it under the door, then you'll go get them.
Yeah.
It's a little easier than putting it in a lab, I feel like, so.
Okay.
Yeah. All right, last thing, which is sort of a downer to end on. But I have one more nice slide after this. So we say this at the start of every semester. Every semester, I hope this will be the one where there's absolutely 0 honor code violations. And for a class this size, somehow that hasn't happened yet. So I really hope this is the year. Please don't do it. For those that need it, CMU's academic integrity policy is here. It says exactly what you would think it would say. Don't violate it. And in particular, this is very important for this class, not because people actually sometimes it's very intentional. Sometimes people unintentionally cheat as well. And this happens most often with this requirement that you have to write things up separately. So just remember that. You have to, you can talk about homeworks in groups, talk about programming assignments in groups, write them up independently. That's probably the #1 cause for honor code violations in most classes. It's just people not doing that. You see 2 identical homeworks that were handed in. So please, please don't do that. If you consult outside material as well, and you are allowed to, for the most part, unless we say not to, unless we specifically say for this problem you cannot consult anything else, you have to list what it is. Okay, so this has become a pretty standard set of requirements at this point. Hopefully you've seen something similar before in a similar class, in another class. But please, it's much easier for us and much easier for you if everything just goes smoothly in this respect. So that, ending on that kind of down note there, I'm going to add a couple parting thoughts about AI in general. These are hard problems, the problems we're tackling in this course. All right, and next lecture rather, we'll talk about in a lot more detail sort of precisely how we'll structure this course and how we'll cover the different topics. But these are hard topics, kind of the hardest topics. And I think this is really exemplified by the fact that in the early days of computers, there was wild optimism that does not even begin to cover how far we've made it. Right? So there's this very famous popular mechanics, which is kind of misquoted, honestly, this quote here. Famous quote from Popular Mechanics saying in 49, saying that in the future, computers may only have 1,000 vacuum tubes and may weigh only 1.5 tons. Okay, so this is appears in some quote every other day, but very famous quote here, and that was already being kind of optimistic at the time. And contrast that with Herbert Simon, who was a very smart guy, right? In 65 said, machines will be capable within 20 years of doing any work a man can do. Right? So we all laugh about how these predictions were wildly inaccurate on the downside. But the predictions in AI are kind of going the other way. I think this speaks to not the fact that these people weren't as smart as these ones. It's just that these are hard problems. And so you will be solving the hardest problems that there are during this course. And hopefully that's exciting to everyone. So hope to see you next lecture.
I have a question about the project.
Yeah. Let me actually wait till he turns off the recording, so you don't get your question heard by everyone. So you could do that too. Good. Okay. So hello everyone, welcome back. Glad to see there's still a lot of people here. Today we're going to talk in a little bit more detail about some of the topics we're going to cover in this course. This will be the last sort of non-technical lecture for this course. We're not going to dive into math yet. But what I do want to do is give kind of a rough overview of all the different pieces we're going to cover and how they all fit together using, for example, this framework of an intelligent agent to describe how they all fit together like that. All right? So again, we're not going to sort of jump into anything in detail, but you probably saw a lot of different topics last time, things like machine learning, optimization, search, NLP, natural language processing, I should say. I shouldn't use abbreviations. Computer vision, these sorts of things. And you might either not really be familiar with them yet, or you might not quite see where they all fit into a big whole. So today, what we're going to do is going to talk about a single example of an intelligent system, or at least a system that we might think is intelligent. And we'll show how different pieces fit into that in these topics I've mentioned, or the topics that are going to be covered in this class. So before that, though, I want to just briefly mention a couple things. This is the website. Hopefully everyone's seen it before. The syllabus is up on this website. So we have a syllabus posted. That includes a schedule for the class. So you can go check that out, have the schedule. I think actually just because it's easier to edit, we might change that to be on the website itself. But that'll be on the next few days or so. For now, it's in the syllabus, this PDF. Second thing, the lectures are available in the lecture tab, and the videos are going to be available here as well. So I think there's been a few views on this, so maybe some people checked it out, the video here. It seemed to be okay quality. Sometimes the first few lectures are bad. I'm a little bit dark in the video. We'll have to make sure when I start writing on the board that you can see what I'm writing on the board, but it seemed okay, especially because I'm not writing on the board in these first few lectures. And they also have, of course, slides for what I present as well. And then finally, just recently, today I posted a copy of the course project guidelines. I was actually going to wait a few more days before doing this, but a lot of people had questions about the course project, so I figured we might as well just do it now, at least get out the basic requirements and the basic expectations of that course project. So those are the 3 additions to the website now. And let's actually just jump right into that last one and talk about the course project. So people had some questions about this. And this is just a very brief description. You should read more about it in the course project guidelines. But essentially, the class projects are designed to be an opportunity for you to dive into more detail in some area of AI. Now, this can either be taking some applied area, maybe in your own research, and applying techniques from AI to that area, or it can be about delving deeper into a specific application of AI and the topics we cover here, kind of core AI algorithms. It's to be done in groups of 1 or 2, so you can either do it independently or in a group of 2. And the final write-up will include, the final report you turn in will include a write-up of 5 pages. You can include additional material in an appendix, and I talk about this a little bit in the description, but the actual thing that we're going to mainly grade is that 5-page final report you hand us. And then finally, again, I think this was kind of common for a lot of these type of classes, there's going to be a poster session in lieu of the final exam. So instead of a final, during that same time slot, we'll have a big poster session, probably in the atrium on the 7th floor of the Gates building here. Okay, so if you have questions about this, that's great. If you have questions about the actual topics of your assignment, in terms of what you want to work on, by all means, come talk to the instructors during office hours. That's what we're here for. If you want to know, is this an appropriate topic? What are some related topics to this? I'm interested in this, etc. Come talk to us during office hours. I guess office hours, Zach will be holding them today after class for an hour. So come chat with us.
It's actually going to be a little bit abbreviated because I just found I have to go up to the UC. So I'll start my office hours at 3:30.
Okay, yeah. So okay. So he's pushed it back a little bit, but it'll be in his office and it's on the website. Oh, also I should mention the office hours. Ours are both up here, mine and Zach's. We did not have the room quite figured out yet for the Tuesday, Thursday office hours. If people really want to go on tomorrow, we have a room reserved. But I imagine there isn't that much to talk about yet at office hours, so we just won't bother with that confusing stuff. We'll just send out an email or just post it on the website when we have the official room that'll last the whole semester. Okay. If you really want to come, then by all means, chat with us. But I imagine talking to TA might not be that helpful yet. We don't have any assignments really yet. Okay, so let's jump into the actual content of this lecture. And to start with, I'm going to recall, not from too long ago, this robot Shaky. So Shaky was a robot I showed a video of last time that was designed to be kind of an office assistant, or at least do work in an office environment. It was sort of playing around in a little toy environment, but the idea of a robot that can do tasks for you is a very common one. And I want to show this video next. This is a video by a couple of grad students at Stanford. So this is, I think, about 2008. Keenan Wyrobek, I think I'm mangling his last name, and Eric Berger, they were members of Ken Salisbury's group at Stanford, and they developed this robot here. And you see it's doing something with a Roomba to sort of kick things off. And the amazing thing is this robot is incredibly capable, right? So it's sweeping the floors. It was replacing the Roomba, right? So that has to sweep the floors. It's vacuuming with an actual vacuum, not a $300 vacuum you have to buy separately as a robot. Here it is, I guess it's cleaning more stuff here, but you'll see in a second it doing a couple more things. Here's emptying a dishwasher. All these tasks require a lot of dexterity to it, a lot of, in principle, require a lot of intelligence in this machine, because in order to figure out what to do here, it has to do a lot of kind of planning, that kind of stuff. However, the big kind of trick going on here is that this robot is not actually acting autonomously. There is a person in like a big cage steering this robot in very precise ways. So here it is cleaning up a room. At the same time, this kind of stuff is really encouraging to us software researchers in AI, because what it means is that the hardware is capable of doing things that are frankly pretty amazing. Right? If I would want a robot that I could let loose in my house and I would come back after the day and it would clean it up. Even if this is 8 times sped up, if we could clean it, while I'm gone and have it be clean when I get back, that would be fantastic. And you see, this is another thing that you might want a robot to do for you. So, again, this is not, while this is a great advance in robotics, if you think about AI generally, sort of in terms of building intelligent systems, there's a lot of kind of control side going on here, but not that much in terms of the actual intelligence of a system being able to operate autonomously. Okay? So now the challenge is sort of simple, right? It's up to us to develop the brains, the smarts for this thing, to actually make it do what we want. This is not a new idea. The idea of a robot butler has been around for a long time, starting, maybe not starting, but at least back to '62, I think, when the Jetsons started. And at the same time, we can think about what would be required for a system like this to execute a pretty simple command. So I'm going to use this running example of me telling this robot, and I'll imagine a robot sort of here in this building. I tell the robot, bring me a cup of coffee in my office. This is not that complex a task, you might think. It doesn't require what we think of as that much intelligence. But let's go through and see what a task like this would require from a robot. And in doing so, I'm going to touch on just about all the topics that we're going to cover in this course. Okay, so this is the table from the syllabus describing the lectures and when we'll give them. And I'm going to talk about how these things all fit into that idea of having this robot go get me a cup of coffee. Some parts here might seem a little bit, some notation, some symbols might seem a bit confusing. Don't worry about that. It is just intended as to situate all these things within the context of a broad intelligent system. Okay, so let's talk about the first thing a robot would have to do. If I tell it, please bring me a cup of coffee, and I'm speaking that, the robot does not get the words, bring me a cup of coffee. What it gets is a sound wave corresponding to essentially the audio fluctuations of me saying this. You can think of this as a bunch of floating point numbers, essentially in series, describing a time series that describes this sound wave. So the first thing we might want to do with a system like this is divide up this time series, right? Because there are some times when we sort of see these little quiet parts in the time series. That corresponds, at least hopefully, to times where we've paused between words. I don't always pause quite enough between words that I say, but I try to pause sometimes. And now the task is for each of these little snippets of sound here, can we identify what word that corresponds to? Okay, now this is kind of hard, right? Because these are all different sizes. And you can think of programming. Programs are very good at running maybe on fixed size inputs. Or you can, if you have a fixed size input, maybe you can just multiply it by some weights. That gives you some output. But for different size inputs, it's kind of hard to think about how do you really process that? And so a very common feature of these type of problems is to use machine learning to help with this. And the first step often of machine learning is to take these different sized pieces of sound and produce a set of what I'll call feature vectors. Okay, so the x's here describe in some sense, we have x1 here that describes kind of this first waveform. Phi of x1 then describes some, and I'll call it even a fixed length vector of features describing that snippet of sound. And we're not going to worry about how do you get that. Actually, for audio, and we're not going to talk too much about audio in this class, but for audio, there are features that have to do with things like spectrograms. These are Fourier transforms of the sound data, things like this, that are very informative to algorithms of what these different sound waves are saying. So then ideally, what we can do once we have these different features, and these are all now the same size, so maybe we can just multiply them all, say, by a vector, phi, And the output we get from that multiplication of multiplying this times a vector theta, that can in some way tell us how we should label each of these snippets. And if we do it correctly, we'll say, okay, this one corresponds to bring, this one to me, this one to a cup of coffee in my office. All right, and while that might seem simple, of course, each step of this is very hard. First of all, how do you determine what features to use here? And then once you have the features, how do you determine these weights, theta, such that the product of these features times those weights gives you anything meaningful? And probably in reality, you actually want several sets of weights, one maybe for each different type of word, maybe not for whole words, maybe just for sounds you can make, stuff like this. So it can get very complicated, but this is the basic idea. Convert to some features, multiply it by some weights, and get out some prediction. So that covers machine learning. Right, that's why you need machine learning. And there's, by the way, lots more things where you could use machine learning. You don't have to use machine learning here, but the problem is once you're at this stage, it can be very hard to write a program from scratch that would give you this sort of correct breakdown here. What's much easier to do is to actually give your program lots of data, give it examples of sound waves that say bring, tell it it's bring every time, and hope that it can learn some weights here that will let it do that prediction in the future. That's sort of the idea of machine learning methods. I'm really showing this just the prediction step here, but the machine learning side is when you actually learn these weights here from a big collection of data. There was a question back there?
Do you mean multiplying each feature by a weight?
Yeah, don't worry too much. So essentially, these have a bunch of features. This theta here is a bunch of weights, and you multiply the corresponding features by their weights, add them all up. We'll get to this when we describe actual machine learning. We'll describe it's essentially a linear architecture, but don't worry about that yet. Okay, so now we cross off machine learning. We've gotten our first bit there. It's also a very popular one, right? Okay, so now I'll add one thing to this, though. It turns out that if you just train a machine learning program to try to predict each of these words individually, these things can do quite badly. Because certain words, or even actually more specifically certain sounds that we make, if you just look at the audio stream, if you were to hear them in isolation, it would be very hard to tell what word was actually being said. What actually lets us let's figure this out as people, is the context in which they're being said. Okay, so the words around it, the sounds around these sounds, actually inform us hugely of what is actually going on in any given sound snippet. So because of this, it's actually very common to augment methods like this with another model, which is called a hidden Markov model. Okay, and in this model, again, don't worry about this here. We're going to learn all about these kind of models and Bayesian networks in general, of which this is one example. But these models, what they say is the actual word here corresponds to this output y. That's the hidden state. Those are the things you do not observe. What you observe are these sounds x. And the hidden Markov model says there is some probability of not only each word generating some sound, but also of transitioning between one word and the next word. This actually imposes structure between the different words. And if you run what's called inference in these models, namely find the most likely sequence of words given the sound you've observed, that can do much better than if you just try to classify things individually. Okay, so this is an example now of another topic here. This is, oops, I shouldn't have highlighted that one. That one's not right. No, that one's there. This is an example of probabilistic modeling, Bayesian networks, of which a hidden Markov model is an example, and then probabilistic inference. So this is actually how a lot of speech recognition programs work. They use hidden Markov models, though there also have been recent innovations as well in machine learning that are making these systems better and better. This one is accidentally crossed out there. We haven't talked about planning yet. Okay, so now we have, hopefully, these words. The next step is to actually process these words in some way that gives meaning to that sentence, right? Otherwise, they're just words. It doesn't mean anything to the robot. The way we can do this is, or one way we can do it, rather, is what's called a parse tree for this sentence. This does not have roots in computer science, by the way. This has roots in sort of grammar and language. But we might say, want to annotate the sentence with a description of what each part is. And this also gives some meaning and structure to this. So what this is saying here is that bring me a cup of coffee. So, for example, a cup together is a noun phrase. This of coffee is a prepositional phrase, which together, a cup of coffee is another noun phrase. Bring me this is a verb phrase, and then this final thing, in my office, is a prepositional phrase modifying that entire verb phrase. Don't worry about this in particular. We'll cover some natural language processing later, but this is an example of things that people do in natural language processing. And to give some idea about why this might be hard, so you might already notice the sentence here is naturally a pretty bad one, right? Because it could mean two things. It could either mean, bring me a cup of coffee, and I'll be in my office, by the way. Or it could mean, we should put the cup of coffee in your office and have the robot bring the entire, crack it out the building and bring the entire office to you. Okay, do people see that possible meaning too? It could mean a cup of coffee in my office, bring me that. And if that sounds silly, think about if I change this to say, bring me a cup of coffee in a thermos. Okay? That obviously means bring me a cup of coffee in a thermos. Doesn't mean I'm going to be inside a thermos and you should bring me a cup of coffee there. So the meaning and parsing of these things actually have to depend in some sense on the higher level structure. This is very much active, ongoing research, but it's really a fascinating thing where even simple things like this, like parsing a sentence, depend on some form of higher level intelligence somehow. All right, so that covers natural language processing, which we're going to do. Moving right on, let's talk about planning. So say that we have parsed that sentence correctly and extracted some logical structure which tells us the goal of the action. Okay? And in typical classical planning, we describe goals of actions as some set of essentially variables that we want to be in certain states. We also know of a collection of variables that we have in initial states, and we have a bunch of these actions described like this. So this is the action called pour coffee. The preconditions for this action are, well, we have to have an empty cup, empty mug, and we have to be in the kitchen. If you don't have those two things, you cannot execute this action. But if you have them, you can execute it. Once you execute it, you no longer have an empty mug. You remove that from your list of predicates, and you add a full mug. Okay, and the goal of planning systems is to take a bunch of these kind of actions, combine them together in a way that brings you from the initial state to an end state. So for example, maybe you have, this is a very simplified version, but maybe if you're in somewhere, a hallway somewhere, you need to bring coffee to me in my office. You'd first go to the kitchen, pick up an empty mug, pour the coffee. So now you have a mug and you're in the kitchen. Go to my office and then give me the full mug. Okay, but coming up with that sequence of steps here, that's challenging in and of itself, right? Because it's intuitively obvious what you have to do to us. But really, if you try to enumerate kind of all the things you could do or all the things you might want to do, this can get very complex very quickly. And how do you efficiently search through spaces like this? Well, this is the topic of classical planning. That's what we'll cover on those days. And by the way, I should also mention, there's lots of overlap here, especially with search and numerical optimization. We're going to use those for a lot of these other things, but I am kind of focusing on parts at a time here. So we don't just use planning for that. We also use search. We also might use constraint satisfaction or other things. But I'm kind of focusing on one element by element here. OK, so that's planning. Next up, we have path planning. Now we have this plan, and we want to execute the first action, which is go to kitchen. Our robot is here, down in the hallway. There's 4 offices here. The kitchen's up in the top right. This one here is blocked by a garbage can for some reason, so we can't go that way. But we can navigate otherwise kind of how we want to in this space. Now, a common way, a very kind of intuitive way of solving this problem then, is to pick a bunch of points in the space and have these be the vertices of a graph. Right? So in this case, constructing these can be hard if you don't know the environment. But if we know the environment, we know kind of where we might want to be, we can construct graphs like this without too much difficulty. So now the question is, how do we get to the kitchen? Well, this is a pretty straightforward problem. You might sort of see the solution, well, it's obviously just go that way. But really, this is a search problem, right? What we want to do is find, say, the shortest path, because we don't want to waste time, find the shortest path from where we are currently to the kitchen. Okay, and the way we do that is via search algorithms. Now, I should also mention, search algorithms actually play a fundamental role in a lot of what we do. So, for example, the way a planner would actually come up with that plan of go to kitchen, then pick up empty mug, then pour coffee, etc., given all those plans with preconditions, with delete lists, and with add lists, the way it does that is actually through searching as well. It's also just a search algorithm, much like this one. You build a big graph, in fact. In fact, you can't build the whole graph anymore, so you have to kind of build graphs and build things incrementally. It's a much more interesting search problem. This is kind of easy to visualize, right, as a search problem. You have to search and find which is the shortest path to this graph here. So this covers, I'm going to say right now we've covered at this point all the search methods. I don't think you'd probably want to use adversarial search to plan a path to the kitchen maybe, unless we'll get to that in a second. Maybe there are other agents that want to interfere with you. But the basic way you can solve these problems is via search. And methods like informed search or uninformed search. Informed search just means that you have some sort of heuristic principle guiding your search if the state space is too big to search to enumerate globally. But these things can all be very, very useful for planning tasks like this. Now, I'll throw in one more twist to the situation here, which I see OK, it's not crossed off here. But what if you know, as the robot, that the professor in office 4 is holding office hours, and he's a very popular guy, so he's going to probably have students outside his office. But maybe not, but maybe, given the time. Well, you can't right now actually see them, so you can't really use your knowledge of where they are or not to plan. So what you actually want to do is use some sort of probability that they might be there, and combine that with the probability of how much more time will it take me to get through if people are in the way, to come up with a different plan. And maybe your other best bet would be actually to go around, to take a longer path to the kitchen, but one that avoids the chance of people being in the hallway here. This is a very simple example, certainly, but this starts already to get to the concepts of probabilistic planning and a tool called Markov decision processes that we're going to use to represent situations like this. OK, moving right along. We're really knocking these off quickly here. That covers probabilistic planning and MDPs. All right, let's talk about vision. We've now gone with our robot. Remember, this is all in service of bringing me a cup of coffee. It doesn't seem that hard. We've now taken our robot and driven to the kitchen. And say we know where the coffee machine is. So we've positioned ourselves in front of the coffee machine. And we have a camera on our robot, so we can look at the coffee pot itself. This one's actually filling up, so you probably have to wait for a while for it to finish filling. But we can see where the coffee pot is. And presumably we want to then pour a cup of coffee. Okay, now the problem here is much like audio, a computer or a computer with a camera does not have kind of a functional description of this scene here, right? All it has is a big array, in fact, a three-dimensional array of width by height by 3 different values, 1 for each color value. So it has a three-dimensional array describing the intensity of each RGB component of this image. Okay, and as you might imagine, it's not always easy to go from those big matrix descriptions to something you can actually use to, say, pick up a cup of coffee, or the pot of coffee, rather. So what do you have to do now? Well, you might want to do a lot of things here, right? We might want to, first of all, try to highlight the pot of coffee in this image. There's lots of other stuff going on too. We probably don't want to grab that coffee pot because it's empty. And we have to know, I know that the coffee pots and gates are coded by their handle. So the red handles are decaf and the black handles are caffeinated. And I would never want decaf coffee. That would be a horrible mistake for a robot to do. So it has to see that there's a black handle, determine the shape of the coffee pot. Maybe even do something like extract a 3D model of that coffee pot, right? Because it has to actually not just say it's there, but actually reach out and grab the handle. So it might need to have some idea about the actual 3D structure of this. This is becoming a little bit easier now. We have now 3D cameras, like the Kinect camera you may have seen, which is actually causing quite a stir in robotics because all of a sudden we can forego a lot of hard work we did before with this nice camera. It just gives us 3D information. But still, it won't give you, the back, and there can be certain occlusions here. So there's still a lot of desire to kind of do things like fit 3D models to images, or now to, I guess, 3D images that we get from cameras. Finally, we might also want to say, where do we pick up that coffee pot? What should we actually do? Presumably we have to reach out and grab it. Should we grab it right there? Probably not, right? We would just sort of knock it over with our less than graceful manipulators like most robots have. So we have to sort of do something like label that spot right there as the one that we want to grasp with our robot. Now, I'm not going to show it here, but just like with sound processing, it turns out that a very good way of doing a lot of these things is to take those raw pixels, those image pixels, which is the raw representation of these images, and extract certain features. Much like extracting a spectrogram from a waveform, from a sound waveform, you can extract things like information about the gradients of this image, so how the pixels are changing in what directions. You can extract edges from them, say which direction the edges are oriented in. And it's people in the vision community over a long period of time have developed a lot of features which are very instructive for tasks like this. They can give us very good performance at identifying, say, where the spot to pick up that coffee pot is. So you probably might also, or not probably, but you might also want to use some form of machine learning on a problem like this as well. Maybe it's hard to know originally, or hard to know a priori, where you might want to pick it up, or how to write a program that tells you where to pick it up. But you could probably label a couple images, pick it up here, etc. That might be a much easier way to accomplish that. All right, so that's computer vision for us, crossing things off one by one. And now we've located the coffee pot. We've fit a 3D model to it. We know where our robot is relative to it. Everything's great. Now we have to actually pick the thing up. Okay, so this, and remember, all for bringing us a cup of coffee. So here we have another problem, which is one of robot manipulation. All right, so say we have this robot arm. By the way, this robot arm looks primitive here. This is, I think, about a $100,000 robot arm. They have a couple down in a lab on the 4th floor of Newell Simon. You might see it doing stuff in that clear. There's a glass wall, and you can see a robot behind it. It has 2 of these arms mounted on it. Maybe they've come down in price a little bit, but they used to be at least pretty expensive, these ones. And so the task now is, given this robot arm, we need to reach out and grab that coffee pot, the handle of the coffee pot. Okay? But of course, we think about reaching out and grabbing something, well, we just do it. That's not what a robot really does, though. What a robot has, what we program a robot, is what we can do is we can tell it where each of its joints should be located. So essentially, this robot here has 7 degrees of freedom. That means it has 7 different joints in its arm. I'm actually not including the hand. We'll just assume the hand sort of opens and closes. But between its arm and the wrist, it has 7 different joints it can move. And all we can do as programmers is set the angle of those joints and change them over time, right? So now the task is, we've maybe, say, even figured out where we want our robot hand to be. We can get that from knowing where the 3D configuration of the pot, knowing where we are. But even that problem actually is tough. There actually are more than one solution, because there's more than we have. The real world, at least the 3D world that we operate in, has 6 degrees of freedom, right? There's 3 rotation and then 3 position. So this robot actually can be in multiple configurations and have the same position of its hand. So it can be hard to even find a single configuration that reaches the end, much less a configuration that will take you from wherever you are currently to that point, by the way, not touching the coffee pot as you go. Right? You cannot touch the coffee pot as you're moving, or you will knock it aside. These robots are very strong. They will knock a coffee pot over without even thinking about it. Literally without thinking about it, I guess you could say. So that's our goal. Move, plan not just one joint angle, because one is just at the end or beginning maybe, but a whole sequence that will take you from where you are now to where you want to be, all without hitting the coffee pot. And a common way of formulating this, so this is, and I should say this is, of course, the robot motion planning problem. If you talk about there being dynamics, so say maybe something's moving that you want to grab, that's now talking about dynamics of control of robotics, and we'll cover both those things later on in the class. One more point, though, is that the way you might actually do this, so the way you actually can go about solving these problems, is by solving what's called an optimization problem. So optimization is going to be a key recurring theme throughout this course. In fact, I'll come back to it later in a second. But one way we could formulate this problem, and this is very high level still, I'm not really telling you how to solve it yet, would be to say we want to find some sequence of joint angles such that, and I guess I'll let that one thing here. I should also say that theta 1 has to be where you start at, and theta t has to be where you want to end up at. So I forgot that constraint there in the problem. But each one of these joint angles you plan has to be in free space. You can't have any collision with your objects in the environment. And given that constraint, plus the 2 constraints that you have to start at where you are and finish at where you want to be, you might want to minimize something like this. So this says, I want to minimize the difference, the squared difference between 2 different joint configurations. And I want to sum the differences up over my whole time there. It's actually very natural. What that does is that encodes smooth motion of the arm. Okay, you can get from here to here in a lot of ways, but I typically kind of go like this. I don't sort of spaz out and go like that, right? I don't kind of make jerky motions to get to somewhere else. Okay, so I think that this is actually a pretty reasonable, and it's very common to treat these kind of problems as optimization problems. It's a very nice framework for dealing with constraints like this, where you have hard constraints. You cannot be colliding, but you also have things that, subject to those constraints, you want to optimize. You want to sort of smooth out your path, subject to the fact that I don't hit anything. That won't be the smoothest path, but the smoothest path that you have might actually collide. So you have to have some balance there. And this is a great example of, this one's up here, of numerical optimization. I'll come back to optimization in a second, but essentially a lot of what we do can be framed as optimization. And what I mean by numerical optimization here is just optimization over real valued variables. So these are continuous variables you're optimizing, which in the case of a robot, you essentially have continuous control over the joints. Okay, now finally, in this task, before I move on to some extensions, I want to talk about reinforcement learning. And here the problem is, now the robot has, so I guess you have to grab the coffee and pour it, which is actually pretty hard in and of itself. But say we've done that. Now we're carrying the coffee back to the office. Well, maybe the robot by default kind of wants to move quickly to the environment, right? That's kind of the default mode of operation. So when we have a cup of coffee now, and we do this, move along at a normal speed, what we find is that we start spilling the coffee. It's not a good thing, especially all over a robot. You probably wouldn't want to spill coffee. So the question now is, how do you design a program that kind of knows exactly what it should do in that respect, in terms of how fast it should go, how fast it can turn, all these things that it can do when it's carrying a cup of coffee or something else, say. And now that's actually kind of much like our old machine learning examples with vision or sound. That can be very hard to write a program just from thinking about it for a while, writing a program that does all this. What's oftentimes much easier is to adopt what's called a reinforcement learning approach. And the idea here is actually very similar to how you would maybe train a dog, right? So I have 2 dogs. We try to train them. They're hopefully well behaved. And when they do something good, we say good dog. When they do something bad, we say bad dog. And the idea of reinforcement learning is very similar to that. The idea is, if the robot comes to my office with, without coffee spilled, then I'll say, good robot. If it spills the coffee, maybe it has to spill the coffee and get to me, and it comes to me with an empty mug all spilled, I'll say, bad robot. I keep doing this. And presumably we know the coffee won't hurt the robot too much. If it breaks it, that's a really bad thing. But we'll assume it can recover from that. But I'll tell the robot, bad robot, you spilled your coffee. Now, importantly, a subtle thing going on here is that unlike machine learning, where we sort of give the right answer at every single stage of a problem, we say this is all, this letter here, or this piece of sound here is always bring, etc. Here, there's an interesting thing called a temporal credit assignment problem. What that says is, we only get we only get feedback from our entire task, say at the very end of our task. Right? We've brought the coffee to my office. It's either empty or full. I'll either say good robot or bad robot. The question now is, how can I take that information at the very end, that reinforcement at the end, and figure out what action I took along that whole sequence of things I did that caused that? Okay, because it's not opening the door at the end that delivers the coffee to me. You don't want the robot to start opening doors everywhere, hoping to get told it's doing well. Right? What you want is to understand that this entire sequence of events, or a sequence of actions, led to that reward at the end. And that's really the challenge associated with reinforcement learning. Okay, so now that sort of covers, I think, most of the task. We have a few other things now left on our list still, so I'll try to come up with ways in which they're going to fit into the same problem, some with more success than others, I think. But for a simple one, I'm going to talk about scheduling. So in this example, the robot I had was essentially given one task to do. Bring me a cup of coffee, and I could ignore everything else in the world once it was doing that. Okay? But now suppose this robot is at the service of all the instructors and TAs in this class. Okay? There's only 3 people, in fact. Imagine if you had even more people. It could even be even more complicated. So now I'm telling the robot, say, I don't know, maybe I tell it at 12:30 or so, hey, bring a cup of coffee to my office in 15 minutes. Exactly 15 minutes, because I'm maybe going to be gone for a while first. I'm going to be back in 15 minutes. Bring a cup of coffee to my office then. Meanwhile, Zach says, I need copies of the class project reports for this class by 1:20. We were handing them back or something, and we have to get copies by then. I can have them before then, too. I'm going to be in my office before then, but it has to be by 1:20. Vittorio says, you know, I'm actually going to need to have this robot show someone else around at 1:10. Meet me in Gates, the 3rd floor in Gates, at 1:10. I'll need your help for about 15 minutes. So one thing you notice is that these times can overlap, right? So it could say, I have to get this before 1:20, but I need to be somewhere between 1:10 and 1:25. So this is a simple example, and I'm sure I actually apologize to Zach for making scheduling out to be something that has these simple problems. But this is sort of the idea here is now we have multiple constraints in time and in resources. You can only be one place at a time. It takes you some time to accomplish certain tasks. The way you coordinate all those things involves problems with scheduling. So this quickly becomes an issue for any system that would actually be doing useful work around an office. Scheduling. OK. The last 2 are a little bit more silly, maybe. But actually, the next one, not so much. The next one says, OK, well, so far we've been talking about a robot that essentially can operate in an environment. Maybe it avoids other people, but more or less it ignores other agents in the environment, other than me, right? It's sort of doing stuff for me, but it's not really adjusting based on what other people are doing, based on what other robots might be doing in the building, et cetera. So imagine instead that you now actually have both a good robot and an evil robot. And the evil robot's trying to somehow interfere with your tasks, right? Maybe it's switching the coffee so that the decaf is in the caffeinated handle. That happens sometimes in Gates. I assume it has to be evil robots doing it, because no one would make that mistake normally. But the idea here is that when you have other, and I'm not going to talk about this in detail at all here, but when you have other agents in an environment, you have to act in ways that will actually take into consideration what they are going to be doing. Right? You don't want to just act independently and have that be that. So we also might want to talk about some things with computational game theory. And how do we deal with scenarios where you're not just, you can't ignore other agents, but you're in fact either cooperating or competing with them. And finally, this one's a bit silly. There's 2 things left over here. And the reality is that constraint satisfaction and integer programming could all be used for plenty of these things. But the typical example people always use for both those things is a simple example. So I'll just say it. Suppose that your robot, after a hard day of work, been working all day, it wants to solve a nice, relaxing Sudoku puzzle. So it's going to do that with constraint satisfaction. This is a very important task for robots to be able to accomplish. It's going to do that with constraint satisfaction and with integer programming. So that knocks off all of them. And by the way, you can easily solve any Sudoku problem, no matter how hard it is, with a simple script that does constraint satisfaction or integer programming. People spend a lot of time doing these things, and I kind of enjoy them too sometimes, but they are really simple for a computer to do, and it solves ones much better than a human ever could. OK, so that is the list of topics that we're going to cover in this course. And hopefully, what this does is give you some sense of how these things, these ideas in AI, both what they are, in case you hadn't heard of these terms before, and I should also add that the things I presented here was a narrow scope of what many of these things are. So NLP, for example, is much more than just parsing. Machine learning is much more than just predicting things for vision or speech, et cetera. But these are at least examples of what many of these topics can achieve in the context of an agent operating in an environment like this. And again, remember, all in service, except for maybe the last one, of bringing me a cup of coffee. All right. So Now we have a quiz. So get out your phones. This is, again, is going to be a little bit, this is an open-ended question, so it's not going to count. Don't worry about getting it wrong. There's no right answer here, actually. But and I'll start publishing it before I start talking too much. OK, so you should start getting notifications now. I mainly want to debug this again because there were some people that weren't getting messages last time. I saw a lot more people signed up for polls now, too. So hopefully, we'll be able to. OK, so 0 votes so far. So I guess it takes a while to check all of them, right? So here's the question. I described back in the planning slide that one action of pour coffee. OK? All right, so this is the action of you're sitting in front of the coffee pot. You want to pick it up and pour it into an empty mug. You start with an empty mug, and you have a full mug at the end. And the question here, which is an open-ended one, and I mainly just want people to sort of get some sense of we'll talk about the answers, essentially, is what I want to ask is, what elements of what we discussed so far could plausibly be involved in a task like that? OK, so we have search, numerical optimization, constraint satisfaction, classical planning. You can read the rest. They all have plenty of application. The question is, for this task, which of these may be involved? And I'll give some time to vote there, because I think that there's lots of right answers here, by the way. It's not just one. Lots of things can be involved. And there's no wrong. I mean, maybe there are some wrong answers, but some things are definitely debatable whether or not this could involve that. And I'm saying reasonably, trying to be loose with my terminology there. Again, mainly here to just make sure that people are able to get the system up and working. Is anyone, by just a show of hands, is anyone not able to vote? OK, good. Yeah, I guess I just had, OK, fair enough. People need more time. Is everyone done? I don't think everyone's done, because 37 votes. More time? Anyone? Show of hands. OK, yeah, at least one. We'll give it to like 21, then I'll give it 10 more seconds after that, so we have plenty of time. Oh, look, 48 votes. So it's getting there, certainly. It's just was maybe chugging along. I think 60 people are signed up for the class on Piazza right now, which is wonderful, because that's the exact capacity of the room. And so that means everyone who has signed up will be able to get in the course, including those on the wait list. I presume that there would be never anyone that would be registered for the class and not signed up yet. They would, of course, dropped it by now, to be polite to everyone. So, OK, I'll give it. Well, it hasn't turned yet at 21, so we'll keep waiting here. All right, 10 more seconds. Everyone set? Anyone waiting out still? One more, OK. Oh, if you're not logged in, we'll try to either get the. I guess it's hard when you're sitting over there. There are a few more chairs over here, so you can probably sit on some more chairs next time. It's a little easier to have your laptop out then. But I think we'll stop it now. It's not going to count this one again. I'm again just debugging this because this is again the last non-technical lecture probably of the entire course. Maybe the last one with presentations too. You don't have to worry too much about the math there, other than your own math and your own presentation. But let's stop it now and close the poll. OK, so here's what people say it involves. And by the way, anyone could vote for both those things. So essentially, this is a percentage of the class that thinks that one is actually involved with it. So first of all, let's talk about robot motion planning. Kind of obviously, right? Yes. The robot planning a motion, grab a cup of coffee, has motion planning components. Someone actually said it did not, right? So someone it only got 96%. It said it involved motion planning. 98%, which I think is everyone but one, and probably there was one with some maybe technical issues. So everyone said that it involves computer vision. That also makes perfect sense, right? Because you can imagine that sitting in front of that coffee pot, grabbing that coffee pot, you're going to need to have some sort of vision there to figure out where to grab. Let's talk about others now. OK, game theory. I don't see how it could involve game theory. So does anyone want to make a case for that? We had 4 votes for game theory. So you don't want to own up to it, it's fine. But if I'm actually really curious how it could involve game theory. Genuinely. How could it involve game theory? No?
The cup maybe is moving.
I see. So someone else is moving the cup adversarially? OK.
Some robots, other robots. I didn't know it.
OK. All right. Yeah. OK. Natural language processing. I'm also not quite seeing how it involves it. But maybe. Actually, maybe you have to read the label or something on the coffee pot to tell it's a coffee pot. Right? It says bun on it, those coffee pots. That's actually pretty reasonable. Is that what people were thinking? That checked NLP, or were they thinking something else entirely? Oh, I see. OK, so this is actually, that's a great point. So he was saying that taking the action, the words pour coffee, involves NLP. So what I was actually asking, and that's a perfectly good interpretation, by the way, but what I was actually asking is the action, calling it an action. Remember, I had that planning action there that was called pour coffee. So what I was really asking about was that action, that description of the action called pour coffee, what should that involve kind of as a subroutine? Presumably, the NLP part would be separate and would be done beforehand to map to that action. But certainly that's a reasonable thing, reasonable thought there. OK, integer programming. If people said it, you could probably use integer programming for this. Actually, I should just go in order here. Scheduling. OK, scheduling. Again, I don't quite see. Maybe if there's going to be some time. I mean, you see any scheduling tasks there? Does anyone want to make a case for scheduling? Yeah.
You have to first put the coffee to get ready and then pick it up.
I see. So right. So maybe I could see it if the coffee wasn't ready yet. And you have other things to do in those 3 minutes. You have to sort of constrain yourself. Maybe. Yeah. Seems reasonable. OK. Reinforcement learning. A lot of people say yes. I buy that too. Right. You sort of want to try things over time. Maybe you're not pouring, sort of your hands shaking. You're not pouring the coffee very well. You want to improve over time. Know exactly how you should control the robot to pour a smooth cup of coffee. Probabilistic modeling and planning. About half the class said that was involved there, and I could see that too. Maybe your actions or your actuator are a little bit uncertain. You can't quite know where you're going to go when you do what you do. Maybe your vision system isn't quite well calibrated with your internal frame of where things are, so there's some noise there. I can buy that, but I mean, so it's also fine if you didn't say that, because it's possibly an important element, not necessarily. Machine learning. I gave the example there about actually machine learning to detect where you want to pick it up. So certainly could, but it doesn't have to. Maybe you could write a system actually without any machine learning that would do this task. That's certainly very, very plausible. Integer programming. So does anyone want to speak up for integer programming? I like integer programming, by the way, but does anyone want to say how they would use integer programming for this problem? No takers. 5 people voted for it, so you're not alone if you speak out. OK. Classical planning. Yeah, I can certainly buy that. Maybe you have sub-actions that you have to step through. Pick up mug, hold mug over coffee pot, or coffee. Sorry, pick up pot, hold pot over mug, then pour. I can see that. You might be able to sort of remove kind of conceptual classical planning from this, but maybe not. Maybe you sort of need sub-actions. You can almost always kind of drill down deeper and deeper with these things to make the next subtask also involve more tasks, et cetera. Constraint satisfaction. Actually, what were people? So a lot of people answered that. What were people's thoughts on constraint satisfaction? Yeah.
When you're grasping your constraint, have your hand touching the handle.
I see.
So that's a constraint in there.
I see. Yeah.
You have
Coffee should not spill.
Right. So OK, those are all. That's actually interesting. I guess I didn't describe constraint satisfaction at all, what it means technically. So I guess, so typically constraint satisfaction is seen as, and I'm just saying this informally now because I didn't describe it at all, it's typically viewed as things where you have multiple constraints you have to satisfy all at the same time, and you have to kind of search and pick things very specifically to satisfy them all. And Sudoku is a great example, because Sudoku, you have to satisfy the constraints where every row has to have an individual number, every column has to have an individual number, and each 9x9 block has to have an individual number. So usually, people think of constraints in that sense, whereas constraints in the sense of you have to be grabbing the mug before you can pick it up. These kind of constraints are typically thought more in line of just robot motion planning. But I think that's actually very reasonable. You could just as easily capture them in a constraint satisfaction framework. So that's actually a very reasonable way of interpreting it too. Yeah?
Constraints to ensure that the copy does not spill regarding the orientation of the top, etc.
Right, yeah. So I again, no, okay, yeah. I agree. I sort of would think of those more as constraints on your configuration space of the robot. But I won't argue that, because I think that's actually very, very reasonable.
Yeah, I think that when you go to constraint satisfaction for the methods,
right.
You'll start seeing that in the technical, so not in the everyday labeling use of constraint satisfaction.
Yeah.
You'll start seeing why those approaches really don't apply to the configuration. So the words are absolutely right, but you'll start seeing the distinction.
Yeah, I think this was a rotten question, honestly, that one, because I hadn't described. I just put up a picture of Sudoku and said that's constraint satisfaction. I didn't describe it at all, or more importantly, the algorithms. But as you said, I think that when you see that, it doesn't quite apply as much, but that sort of only becomes apparent when you delve into the technical details of things.
So one of the things, just real briefly, one of the things that backs up all of this is you have to understand a world model to the extent that you have to do with tasks.
Mm-hmm.
And some of the things that are helping us are machine learning techniques, like learning reinforcement learning. And those are ways to sort of do it by sort of repeated tasks and learning. Another way is that, as he was talking about, you might be able to do it without doing machine learning.
Right.
Which might be you just code the model up to the point that you go by taking your own knowledge and putting it into your knowledge.
Yep.
This is a big issue in learning the world speed.
Yeah.
And so when you start seeing constraint satisfaction, what you're going to see is that it'll only apply to certain types of things that we can represent in the world model. The techniques don't understand very well.
Okay. Yeah. So and I'll talk about a little bit more about this sort of the formal framework for intelligent agents in the next few slides. But okay, moving on to numerical optimization, and usually the answers to these things won't take quite so long because usually they are, here's the right answer. This is sort of very fuzzy. This one I actually had hoped more people would say yes for, because I actually gave an example of numerical optimization in the task itself. This is the one where you minimize the difference in joint angles subject to these constraints you have to be in the non-colliding space of the robot. So definitely this one. I guess you could do it again maybe without that, but you probably want to use something like that. And then search, again, about half say yes, but certainly you can use search, right? You could maybe plan an initial configuration of angles by a search method and then smooth it with a numerical optimization method and things like this. Okay, so I mean, I think that there's a general consensus on some. Some are also a little bit, people are unsure. Some are pretty clear that it doesn't quite fit in there. But I think that it goes to show, more than anything, that all of these tasks, not just the whole task of getting a cup of coffee, but all these, even to pour coffee, involves a huge number of different components in AI and can bring these all to bear on a problem like that. So that is then the plan for the course, right, to talk about these things. Now, I want to step back a second, and yeah.
Don't you think that search is a part of robot motion planning?
So search is used absolutely in robot motion planning. Search is also used in classical planning. Search is also used in integer programming, in what's the list of these things here? Okay, so search is going to be used in constraint satisfaction, classical planning, integer programming, probably machine learning, probably probabilistic inference, computer vision, scheduling, and robot motion planning. So this is not a disjoint list here. And really, search and numerical optimization, I guess it's the same thing about numerical optimization. They're used in all these areas. So it's absolutely true that you use search in that, but search is not a subset. I mean, search is not constrained to this. It is a general technique that will be applied to many different areas here. Okay, so now let me step back a second and situate what I've presented so far in the context of what we're calling an intelligent agent. I think we'll get to that point on kind of the world view and world models, etc. So when you read the second chapter of Russell and Norvig, it's called Intelligent Agents, and their conception of what AI is, or at least I wouldn't say that, but the way they present a paradigm for AI in that book is that they do it in terms of these intelligent agents. It's a very useful paradigm. I don't think it's quite the one that we're going to follow, so I'm going to make a case for it, but then also a case for other possible paradigms. But the paradigm here is that you have an agent, which is the system that you are creating. So that this would be that assistant robot you're building. It has some actuators which can cause it to act on the environment, and it has some sensors which perceive the environment. Then you take the sensors, take the input from the sensors, do something. They just actually have a big question mark here, but you do something internally. That's the software, it's the programming, it's the guts, I guess the mind guts of the machine. And what it spits out is what to do with the actuators. All right, so in some sense, that sort of makes the problem very simple, right? What a robot should do, what a butler robot should do, is listen to its sensors. I mean, listen to what I'm saying, to its audio sensors, to its camera, look at its camera, and then just move its joints in response to this. Right? You're done, right? You can do everything. You just pick the proper joint motions from whatever current input you see in front of yourself. Now, in reality, if you were to try to sort of, code up a lookup table for every possible, say, thing you could see and what action you should take, that would be impossible. You can't condition every single sequence of audio bits you could ever hear, or what, total amount, every single possible image you could see. It's not possible. So that's why I think people have developed more sophisticated frameworks for this, because this doesn't really say much here. I'm not going to go through them at all. It's definitely worth, this is our textbook. It's worth reading the second chapter in this book to understand this framework. I will give one example now of one type of agent that they use. This agent is called a model-based, goal-oriented agent. So the idea here is, how do you accomplish these things we set out to do? Things like bring me a cup of coffee, know if you've done that well or not, I guess. And one very common way of doing it is to take your perceptions, your sensors, and somehow filter them to give you what I'm calling a world state, a representation of what the world is like, at least what your own little world is like. So for a robot, maybe this would be, where it is in the configuration of an office, maybe what its current tasks are that it has to do. Well, I shouldn't say what its tasks are. That's more about the goal. Maybe something like what it has. Does it have a coffee mug or not right now? That all is filtered together to give the robot its state. Then you also have a model. And that's the box here that I'm calling how the world evolves. You also have some internal model that says, if I take some action from some state, what will my next state be? Right? So if I am in the state of kitchen, empty mug, and I take the action, pour coffee, I will now be in the state kitchen and full mug. Okay, so that's the internal model. That says, how does the world evolve? And by the way, as was pointed out before, you don't have to act this way. Right? You could just be completely independent of any model. You don't have to have that. You could just have some lookup that says, given these inputs, I'm going to do these actions, and magically it would somehow pour the coffee. But I think this is a pretty nice paradigm here, right? We think of having some notion of the state of our world, right? We think that we are somewhere in space and in time, and we assume that if we do certain things, it can change our state in certain ways. This is a pretty nice model. Then, that sort of, those top four boxes are the model. And I should really call this probably hypothetical next state, because it's not that we're going there next. It's that if we are in a state and take some action, our model tells us we will be in state Y. Okay? Then what we have is we have a set of goals. These are the states maybe we want to be in, that we want to gear or drive the system towards. Maybe it's just sort of something like we want to do this quickly, we want to do a minimum time to get from this state to this state, etc. So we have these goals in addition. And what the agent does now is that it uses our predictions of the next state along with these goals to determine what to do next. And this is a fairly simple drawing here, right? Because it could be that you actually look at many future actions, not just the next one, but you look at many future states. You also probably would look at then, what next state do you actually get to if you take these actions, etc. So we might use sort of several next states. But the idea is, using our internal model, we kind of simulate what would happen if we take these actions. And then we take the action that achieves our goals in the best way. So it seems like a simple paradigm. It's actually a very useful paradigm for how an agent should behave, right? It thinks about what's going to happen, thinks about what's going to happen sort of rollouts from now, thinks about its goals, and chooses actions to kind of make those goals happen as much as it can. Similarly, just takes and then takes actions and then perceives what happened, and repeats this loop. So I think this is actually a very good paradigm for how a lot. Yeah, question.
Why does it do the action after it predicts a set of possible actions?
So what it will do is it will sort of take every possible action. So what the robot, or in its own head, right? So if the robot wants to plan a path, it sort of says, okay, if I go right, what would happen? If I go left, what would happen? I'm going to follow both those plans because I might not really know what to do until the end. So I'm going to follow both those plans. Maybe hypothetically branch at different times so it's until I reach the goal in some of them. And then I'm going to look back and see, well, what's the first thing I should have done to really do this whole thing the best? So these next states are really kind of hypothetical. They're done internally using the model in order to guide future behavior. That's sort of, it's not obvious from this figure too. This is kind of a simplification of the figure, but that's kind of the basic idea. Is that the next actions are kind of hypothetical, and you take them in your head, and then execute them only when you found the best ones. Possibly changing along the way as you go if they end up being invalid or something. So I think this, as I said, this is the paradigm for how, or this is the paradigm in which they explain a lot of AI in the Russell and Norvig book. I think it's a very good way of explaining it. I don't think it's really what we're going to at least come back to again and again in this course, because I think the reality, for better or worse, is that a lot of AI research has focused more on solving very specific problems rather than the overarching goal of creating an intelligent agent. Now, these goals are often still in service of a potentially intelligent system, but you see a lot more papers, for example, on better vision systems instead of papers on taking a vision system and a natural language processor and all these things together to build a robot butler. There are efforts to do that, by the way. There are very much ongoing efforts, but I think when you work in a lot of areas in AI, you will end up kind of focusing on maybe one or two of these tasks. And you sort of focus on that task and you solve that one problem. So both are good, by the way. I'm equally happy with both types of research. But I want to at least present the fact that AI actually can be more about solving certain problems. Just solving certain subsets, doing it really well. It doesn't have to be in service of this huge overarching goal of a general intelligent assistant. So let me propose a different paradigm. This is a very much kind of a functional paradigm. Shouldn't use the word functional because it means something very specific in computer science. This is sort of a practical paradigm for what people actually do when they do research in AI and when they build AI systems. And this sounds kind of maybe a little depressing. It isn't quite as grand as building a general purpose intelligent agent, but building AI systems, if you do this, you will solve a lot of optimization problems. You're not going to get away from that. Now, I'm meaning optimization there very broadly. I don't just mean numerical optimization. I mean optimization. So first of all, let me say what I mean by that, optimization. So what I mean by optimization is, I don't mean, nor do I mean like optimizing your code to run faster. That's definitely not what I mean here. What I mean is, you have a set of variables that you want to find the value for. Okay? The way you have an objective, f. The objective takes as input, and I'm not writing kind of the formal math here just because we'll have plenty of that later on in the course, so I just want to get the high level here. You have an objective f. The objective f takes as input the variables and produces some real valued number. Furthermore, you have a bunch of constraints, a set of constraints C, which is some subset of all the allowable variables x. Now, what optimization is in the context of this class, when I say optimization, what I mean is solving problems like this. Solving a problem where we minimize over x, that means we choose the x that minimizes this objective. You can maximize too, but you can also just minimize negative x if you want to maximize. So talk about minimizing f of x, subject to the fact that x has to be in these constraints. Okay, so that is what an optimization problem is in the context of this course. And in fact, we've already seen several examples of this. One example, which we saw before in robot manipulation, is this problem here. This is sort of obviously, I mean, I even wrote it in the same form, right? Our variables here are our joints for our robot, all of the joints, and in a sequence of joints. So optimization can take place over time, too, by the way. These variables can correspond to states at different times. Minimize some function of these things, I guess in this case sort of optimizing smoothness of the trajectory. Subject to our constraint here, the constraint being that each of these things has to be non-colliding with the environment. So that's kind of obviously an optimization problem, right? Here's another one, and this is really any search problem. Can also be written as optimization. Now, I should actually step back a second and say, there typically is a big distinction between when you're optimizing over continuous variables versus over discrete variables. Typically, we will use methods from search to solve discrete optimization problems and methods from numerical optimization to solve continuous variable optimization problems. But fundamentally, kind of conceptually, they actually can be written in virtually the same framework. So here's a planning task in a graph. We have a set of vertices, and then we're just going to label these 1 to n. And this is our graph here describing our layout in the office. And we have a bunch of costs, C, I, J. This is the cost, say just the distance would be the simple one if you go the same speed at every spot. This would be just the distance between this vertex I and vertex J. So for this cost here would be however long that is. This one here would be infinite. If there's no edge between two different nodes, you can't go along that path. That would be an infinite cost. And the question is, well, what we want to minimize is L and V1 to VL. L here is the length of the path. It's how many actual points you have in your path. So here actually the variable you're optimizing over is variable length. Optimize over L, the number of points in your path, and then what vertices those are. The cost of going from one vertex to the next one, subject to the fact that the first one has to be the starting position, the last one has to be the end position. Okay? I mean, this is sort of almost trivial, obviously, but it's very sort of useful to think about these problems, these graph search problems, say, in terms of this framework of optimizing an objective rather than just solving a problem, right? It's really nice when you can think about it in terms of we are minimizing this. There are lots of possible paths. We are finding the one that minimizes this. And finally, machine learning, which there was a lot of interest in last time. I'm running out of time, so I don't want to spend too much time on this certainly, but essentially a lot of machine learning is also framed as optimization problems. At least building machine learning algorithm or machine learning models is often framed as an optimization problem. And here's one example. It's a very generic example, but the idea is with one class of machine learning methods called supervised learning methods, the basic setup is that you have a bunch of input points and a bunch of outputs, and you have, say, m of these, and you have some hypothesis function. The goal of training a machine learning model is to, oh, I actually didn't say what theta is. Theta here is what the parameter you're trying to optimize over. So I should have also probably put theta there as being parameters. But the goal is to achieve your outputs being close to this hypothesis function applied to your input. And a common way to do that is to optimize the squared difference, say, between these outputs and what your hypothesis says. And we're minimizing this over theta, which are the parameters of the model. Now, we will cover this in much more detail in the 2 lectures on machine learning. But this is sort of a basic setup for machine learning. And it kind of also drives home why optimization is really at the core of a lot of machine learning. So this is the plan. It is ambitious. There's a lot of things here. And so, we're not going to cover them, as I said, in as much detail as you would get in a class on computer vision. But you will learn a fair amount about how we would do a lot of those things you need to build that robot assistant. And I think that hopefully everyone will stick around for all of that. I should also say, this is, as I was saying at the beginning, this is probably the last non-technical lecture. So starting next time, we will dive into search. There's actually already been a change. I think we're already flipping one of the search ones due to some scheduling. But we'll dive into search next time. And we'll start talking about the math of how you actually solve problems like this to address tasks like you saw in the lecture today. Thanks.